So now let's actually calculate the work done by the spring. So in scenario A, the spring is placed horizontally, and we are going to push the block for a distance L. So because this is the natural length of the spring right now is compressed by L minus X. So the force on the block is the spring constant K times the compression length. And this only works for X smaller than L because as X reach L, the block will just fly away and no force will be applied on the block. So let's calculate the work. It will be the force integrate with distance, and in this case the force is K L minus X, and we are going to integrate from 0 to L. So the first term gives you just K times L squared because it's a constant. The other term will give you a 1/2 for integration. So the work done by the spring is 1/2 KL squared. The kinetic energy of the block originally is 0 because it's not moving. And then after the spring do some work, the work is going to increase its kinetic energy. So this is the final kinetic energy, which should equal to 1/2 mv squared. So we get that 1/2 mv squared equal to the work, which is 1/2 KL squared over here, and therefore we get that v squared should be KL squared divided by n. We can take a square root and get the final speed of the block. For scenario B, we are pushing it diagonally, and the spring is going to reach a natural length of 2L. We know that the spring will push the block until it is square root 3L, and in that case the spring will be 2L in its length. Now the length of the spring when here the block is at distance x from the original position can be calculated using Pythagoras theorem. So the compression of the spring will be the total natural length minus the length that it currently have. So this will be the force acting on the block. But the force is going in a diagonal direction, so we want to take the horizontal component to calculate the work. This horizontal component is making an angle that is the same as this one with the horizontal line. So we can have the x component of the force be the force itself multiplied by the cosine of this angle, which is x over this square root. So it will be multiplied by this factor and this is the horizontal component of the force. So now we can calculate the work. It will be the x component with dx, and this time x will go to square root of 3 times L. So this will give us a term first, that is the force. The force is K times this factor. Let's do it over here. This is the force, and to take the x component we need to multiply by this factor. So there will be two terms. The first term is going to have some constant, and then this integration with the hint given here by the problem statement. And the other one will be a really simple one with just x dx because the square root cancels each other. So we can do the integration. The first one is given by here. We will have the upper limit to be square root of 3L plus x squared, and the bottom limit to be 0. Note that in this case, the bottom limit will not give you 0 because there's an L squared in the square root. And we need to subtract what we get from here. This will give us 1/2 kx squared with upper limit square root 3L and 0. So the first term with square root of 3 in here will give you 4 in the square root, and 4 square root gives you 2, so we will have 4k L squared. And when we plug in 0, this term will be 2k L squared, so the first term itself will give you a 4kl squared minus 2kl squared. This term will be 3 over 2 kl squared, and after you do all the fractional number calculation, you will receive 1/2 kl squared, which is exactly the same as scenario A. So this will also be the speed of the block in scenario B.